the legs. 1, 2, 3, 4, and 5 legs. Now, yeah, this leg was photoshopped in, but I am going to show you some pictures of real mutations today. But this is the general idea. So, going through some basic information before going into it. DNA and chromosomes. DNA are made out of proteins, chromosomes are made out of proteins and coiled DNA. We've talked about this before, where you take your DNA and you cut it into 46 pieces, 46 chromosomes. And then those pieces get kind of twisted up, braided up, tied up for, packaging purposes, keep everything organized, and they're going to be held in that braid by proteins. Each chromosome has 2 helices because you went through mitosis, DNA replication. Mitosis is next chapter. You went through DNA replication. So now you have 2 strands of DNA. So this is going to be 1 strand, and this is the exact copy of the other strand. They both say the exact same thing. Remember this for next chapter, guys. Next chapter is going to be all about separating these. This will be in one cell. This will be in another cell. Future reference there. And what you are seeing is when you say 2 copies, I don't mean these 2. I mean this side and this side are identical. This and this are identical to each other. But this whole X, this chromosome, and this chromosome are not identical to each other. What you are looking at, ladies and gentlemen, again, information for a future chapter, is your DNA that you got from both of your parents. So you got this one from, mom, then you got this one from dad. And they're both talking about the same aspect of your body. If this one talks about your eye color, this one also talks about your eye color. Maybe this one says you have brown eyes and this one says you have blue eyes. In a different chapter, we'll talk about why one will win over the other. But you will probably have brown eyes. Remember that, for instance, for coming up, there'll be a picture of a cat with like a yellow eye and a blue eye. They're both in there. It's a mutation if they both show up. And maybe this one's talking about hair color, and this one's also talking about hair color, say blonde hair and red hair, and you have blonde hair. You still have the code for red hair. It's all in there. Mom gives you something, dad gives you something else. Right. So, one section of DNA is known as a gene, as shown in this picture, right? Only this little part that we care about is coding for one protein of your body, or as we're going to call it, a trait, because that protein is going to become a body part. It's going to have something to do with a trait, and a trait is something that we can actually see, like hair color, skin tone, your height, the shape or size of your nose, or the shape or size of your chin. These are all traits, and they have to do with your proteins. Now, these are going to be 2 new words, and they weren't even vocab words. These will be vocab words in again, different chapter. We're seeing a lot of future stuff right now. Genotype and phenotype. Genotype is the gene sequence right here. It tells your body what to look like. Phenotype is the actual physical trait, what shows up. So your genotype might include 2 different eye colors. Your dad said brown eyes and your mom says blue eyes. You have both of them, that is your genotype, but only one actually shows up on your face, and what actually shows up on your face is the phenotype. And what we're talking about is if we mess up that genotype, we can mess up the phenotype. That is a mutation. Not the phenotype, but the genotype. You mess up the genes, that's a mutation. When you mess up the phenotype because of the mutation, that's disability or disorder. There's another word for it, but I'm blanking on. So anyway, quicker rundown, less quick rundown. One gene or genotype makes 1 strand of RNA. That's what we've been talking about. RNA is going to be used to make proteins. Polypeptide chains there, but made use proteins. Those proteins are going to build up your actual physical body. Different proteins have different jobs to do. That's when things go right. When they go wrong, up here, that's a mutation. So, what do we know about mutations? Probably incorrect things. Take a look at this picture, guys. This is an older picture. I doubt you guys even care about the old Marvel movies before Iron Man came out, but before that, X-Men were big. And turns out X-Men are wrong. That is not how mutations actually work. In the X-Men, they make it seem like, oh, you got a mutation. That means you gained some kind of cool trait. You know, Wolverine gained claws coming out, or Cyclops gained the ability to shoot lasers. No, that's not how it works. You don't gain new things. What a mutation is a rearrangement of what is already there. So Wolverine's healing ability, that could be a viable mutation because we all have the ability to heal, but his mutation may cause it to speed up. That makes sense. Or Beast over here in the background, we all have hair. His mutation happens to have him grow hair faster and in more places. That's actually a real mutation that does exist. There's like a famous guy with that mutation. They call him the Wolfman. We all have the ability to build muscle. He does it faster and better, so he's stronger. Being blue, that's not a thing. In reality, he would be brown. You know, growing wings, not going to happen. Shooting ice, not going to happen. Right? We are not going to gain new information. However, changing what is there, which is a mutation, may actually end up being a good thing. That's right, guys. Sometimes it's a difference, but sometimes that difference can be an improvement and not a detriment. What we're looking at right now, guys, is the result of millions of years of evolution. Now, if you're going to start arguing with me about evolution's fake, it's just a theory, I don't listen to it, that's fine, guys. Believe what you want. I talk about evidence of evolution. And there is a tremendous amount of evidence, which you can't argue. Evidence is a fact that's there. There's a tremendous amount of evidence that suggests that humans, cats, whales, even bats have a shared ancestor. And some of the evidence is shown in this picture here, in that we have the same bone structure. But through maybe years and years of mutations in one species, they changed a bit and became a good thing for their lifestyle, was an improvement. So for instance, take a look at the human arm here. We have a humerus bone. A cat has the same humerus bone, shaped slightly different for their lifestyle. A whale, oh, my mouse over here. Whalebone, humerus. Bat, humerus. They're just all shaped differently for their lifestyle. Forearm, radius and ulna, radius and ulna, radius and ulna, radius and ulna, same thing. Even down here, all of these finger bones. Guys, why would a whale have finger bones? It's useless. They don't have fingers, right? It would make more sense to have one really big bone. But no, they have finger bones because possibly they had an ancestor that actually needed fingers and a mutation that prevented the skin from receding. That's what happens to us, by the way. We are born like, not born, we are grown like, as a fetus like this, where we have just like a flipper and the bones on the inside. And as we develop, the skin recedes down in between them, showing the fingers, developing the fingers. And there are mutations in humans where that doesn't happen and you're born with a flipper. If you happen to be an aquatic animal like a whale, that's actually an improvement. Here's another example of that happening in mammals. Oh, whale is a mammal, but where that skin is supposed to recede down your limbs, so you have individual limbs, but in this flying squirrel, they didn't recede. And instead of being a detriment, it actually was an improvement. They've learned to use it to glide from branch to branch, and they became more successful. They were able to get around faster, get food faster. They were healthier because they had more food than other squirrels of their species starved and before they could pass on their genes. So these guys are the only ones breeding, so now they all look like this. So mutations can lead to great changes. Sometimes they're also a detriment, like these guys. This one was photoshopped, but this one is real. You know, there is a mutation where instead of all the information for developing a head accidentally got doubled up, and now you got two heads. And this does cause problems. It's been known, these snakes have been known to go and try to go in two different directions and actually cut themselves right here. This one, again, real picture. Sometimes information from both parents show up when only one is supposed to show up. Maybe dad had rounder ears and mom had pointier ears. One is supposed to win out over the other, but there can be a mutation where they both show up. And no, I don't know if they're both sets are usable. I think one might just be cosmetic. And this is another very common one. This happens in all species across the board, at least all mammal species that I've seen. Like I said, maybe dad had information for the yellow eye, mom had information for the blue eye. Instead of one winning out, they both show up. So this is actually not a detrimental mutation. It may actually, other cats may actually find that attractive and be a good thing, help find a mate. You don't know. That's what happened with blonde hair. Blonde hair was a mutation, but people found it attractive. Red hair was a mutation that people found it attractive. So it became a good thing and spread. All right, so how do these mutations work? Oops, I forgot my pictures were changing. All right, it is going to be a change in the DNA sequence. Here we have DNA. But if you get the wrong base in the wrong spot, instead of an A, you get something else, which is usually a mistake, then you're going to get the wrong code. It's like spelling a word wrong. I meant to spell cat, but I accidentally spelled hat. So instead of requesting a cat, I got a hat, and I don't want a hat. And the DNA is wrong. The RNA, like we said earlier, the RNA will be wrong. If the RNA is wrong, the amino acids will be wrong. And if the if the wrong amino acid is picked, then the protein will be made wrong. Oh God, it's just getting worse and worse now. If the protein is made wrong, then the phenotype has a defect. Defect is the word I couldn't think of earlier. If the DNA is wrong, it's a mutation. When the body is wrong, it's a defect. So everything depends on the DNA being right in the very beginning. It's like whisper down the lane. If the first person messes up, everyone messes up. So let's talk about different kinds of mutations. And no, guys, I'm not focusing on body defects, although I do have a few examples. I'm talking about genetic mutations, the genes, and that's what we're looking at, genetic code. Our first kind of mutation is called a deletion mutation, where one or more of the bases are missing. So this is actually an RNA code, because if the DNA is wrong, the RNA is wrong, right? So for whatever reason, that base was gone or deleted. Never showed up in the first place. Now here's the important part, guys. This is going to be important in a little bit. We do not leave empty gaps in your genetic code, right? So everything shifts over. Why is that important? Because everything RNA is read in codes of 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So we were supposed to have AUG, CCC, AAG. Now what do we have? Instead of, what was it? I've already forgotten. AAG, now we have AGA. That's the wrong code. We were supposed to have AAG, then ACG. Now we have CGA. So everything afterwards is wrong. That's going to be one of our words coming up. Right now, though, this act is a deletion. That's it. One or more bases are missing. So I don't remember if I filled this in for you on the digital version. I think I did. And an example of this would be hemophilia. Whoops. Hemophilia. If you don't know what this is, that is when your blood does not make a scab. Normally, you have these things floating around in your blood called platelets. We'll learn more about those in anatomy class if you take my anatomy class. When you get cut, the blood pours out, and these little platelets fill in the gap, and everything hardens up. It grabs some red blood cells that fill in the gaps between the platelets, and you get a scab. If you have hemophilia, you don't have enough platelets. And then they don't make a good scab, so you just bleed right through it, and you keep bleeding until the skin heals or the blood vessel heals. You bleed the entire time, so you have to be like bandaged up, and maybe you can get blood transfusions. That's because all of that, one little scrape, and you got to go to the hospital and get blood transfusion because you're missing one base. That's all it takes. Another kind is the exact opposite. It's called an insertion mutation, where same original code, but instead of losing an A, we're going to jam a C in there. So one or more extra bases that should not be there. And we get the same or similar problem. We were supposed to have AAG, but instead we get ACA. We were supposed to have ACG, instead we get GAC. Everything afterwards will be messed up. Example of an insertion mutation, all because one extra base got added, which we call a nonsense mutation, which we will talk about. This is where you accidentally get a stop codon way too soon. UGA right here, that a stop codon, it says, okay, you're done, but you're not done. UGA was supposed to be further on. So we're going to be missing amino acids because we stopped too soon. This causes something called Huntington's disease. All right, this is a brain. This is a normal brain right here. This is what your brain's supposed to look like. If I were to take your whole brain and cut it up like slices of bread, this would be one slice of your brain. And notice that there are small gaps in between, you know, where the folds are. And this is here where nerves and blood vessels are supposed to be moving around, coming in. But look over here with Huntington's disease, because you stopped making your DNA too soon, then you didn't make your brain well enough. The proteins that are supposed to be here are incomplete, so your brain doesn't develop well. And these people, unfortunately, do not really live past childhood. And while they're alive, they have severe defects. So not a great thing. And then we have a substitution mutation, where one is replaced with another. So it's kind of like deletion and insertion at the same time. You delete one, but insert another one in its place. That's it. So you're supposed to have an A right here, and instead you put a U. Gap is filled though, so nothing else after here changes. This is the only change. So you're only going to mess up one amino acid, which I guess not as bad, but still bad. And this will result in what we call a missense mutation, where we get the wrong amino acid because we got the wrong code. So remember, nonsense, you stop too soon. Missense, you keep going, but you got the wrong code. And this can cause something called sickle cell. You may have heard of sickle cell anemia. Anemia, by the way, is just when you don't have functional red blood cells. Sickle cell is a specific kind of anemia. Because you got the wrong code, you made the wrong protein, or you made the protein incorrectly. So that protein was for your red blood cells, and then they get shaped wrong. The shape of your red blood cells is actually important, right? They're supposed to be kind of like the lazy river. You sit in a round float in the lazy river at water parks. So when you hit a bend, you hit a curve, you take that curve a bit easier. But if it's flattened, one, it's not going to do its job. Its job is to carry oxygen, right? If it's flat, it carries less oxygen. That's bad. Second, if it's flattened out, then it can't take the curve very well and gets stuck, and they all pile up, and you get a blood clot. And that can build and build and build until your blood vessels rupture and you bleed on the inside. Remember, just because blood's in your body doesn't mean it's in the right spot. It needs to be in your blood vessels. If it leaks out of your blood vessels, you're still bleeding, even if it's inside. All right. At this point, what we just talked about were three kinds of mutations: deletion, insertion, and substitution. Now, we're going to talk about results of those mutations. Like, what else can that mutation cause? The first one here is a frame shift. That's what I showed you with the deletion and insertion. Yeah, you messed up one base, but everything after that got messed up too because they all then move over. I delete that A. Look at it again. codes of 3. 1, 2, 3, 1, 2, 3, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I get rid of that A, we don't keep gaps, so everything shifts over into the wrong frame. That's what we call this. In between these lines, it's a frame, and they shift over a frame. So instead of AAG, ACG, we get AGA, CGA. Instead of AGA, we got GAC. Instead of CUG, we got nothing because a codon needs 3. So this isn't even anything. Everything afterwards gets messed up. That's a frame shift. Same thing with an insertion, everything shifts the other way. So this is just everything I just said in a different slide. Frame shift. Everything after the mutation is wrong. Another thing, I already mentioned this one, missense. This is when it doesn't matter if it's deletion, insertion, substitution. If you get the wrong code, you're going to get the wrong amino acid. We call that a missense. Here's how you're going to remember it. Missense because you misread it. You were supposed to get one amino acid, but you gave it a different amino acid because you misread something. So now you got the wrong code. Example here, you're supposed to have ACG, instead you got AAG. So ACG, if you look at your codon chart, which you don't have to right now, just take my word for it, it asks for threonine. But because you got the wrong code, you misread it, you get AAG, you ask for lysine instead. That's the wrong amino acid. That's like saying, I need a brick for my wall, but instead I get a piece of styrofoam. That's not going to support anything. My wall will be built wrong. It will probably fall over. It will not be structurally sound. Nonsense mutation. Like I said earlier, it's when you accidentally get a stop codon too soon. UCA, I don't even remember what it asked for. It asked for some amino acid. But instead you get UGA, which is a stop codon. So now you get one amino acid and then you stop. That's your entire protein, one amino acid. That's nothing. So you stop too soon. That's nonsense. Non as in no. Stop working, don't work. All right, and then we have what is my personal favorite, a silent mutation. What is a silent mutation? That is when nothing bad happens. Seriously, check this out, guys. Serine. You get 1, 2, 3, 4 different codes shown here that will ask for this amino acid, which means you could mess up and still get the correct amino acid. If you're supposed to have UCU and you accidentally put UCC, okay, you still got serine. As long as your amino acid sequence is correct, nothing bad happens. You still technically have a mutation because you got the wrong code, but you didn't get a defect. Everything was still built correctly. It's like saying, I need a red brick. But I said it wrong. I spelled it wrong. Maybe I spelled red as in I read something, R-E-A-D. But the body still knew what I meant and still gave me a red colored brick. Yeah. So everything works out fine. So again, I got a code. CCC asks for, let's see here, first base, C, second base, C. So they meet up right here. CCC is proline. Instead, I get CCA, which is still proline. Cool, I got a proline, I'm good. No one panic, your body's fine. That's a silent mutation. They both go for the same thing, so nothing bad happens. Got the correct amino acid, so the protein's built correctly, all good. By the way, guys, if I'm going too fast, please feel free to slow me down. Ask me to go back a slide, whatever. I only got one more slide left anyway. Environmental influences, things that could cause one of these mutations to happen. Remember, I said mutations usually happen during DNA replication, right? Well, here's things that could disrupt that replication. Taking drugs, because DNA replication is a chemical reaction, and drugs are chemicals. So you throw more chemicals into the chemical reaction and you can mess up the reaction somehow. Alcohol, also a chemical. Now, a little alcohol is not going to cause cancer, obviously, but excessive alcohol, like we're talking a lot of alcohol on a daily basis, can mess up the DNA replication in your liver, and you get some major liver problems. Cigarettes I already talked about. Again, chemicals, pesticides are chemicals. All these chemicals, and pesticides, by the way, I mean like the stuff that they put on the on farms. They put it on all the food. That's the reason why you're supposed to wash your apples before eating them. You're supposed to wash all of your food because there might be pesticides on them. Side note, if you eat organic food, that's not what organic actually means. We'll talk about that some other time. But what they mean is they didn't put pesticides on it. So you really don't have to wash it. But also, there were pests all over the food and probably ate most of the food, so they can only sell a little bit of it, so they had to crank up the prices. That's all it means. If you wash regular food, it's just as healthy. Don't worry about it. All right, another thing that can cause it is radiation. Like, yeah, nuclear radiation, because it's energy, and energy waves of vibrations and wavelengths, things like that, can get in the way of making the bonds. Solar radiation as well, UV radiation, mess up DNA replication in your skin cells, giving you skin cancer. All right, so remember that. Things wrong in the DNA, wrong in the RNA, wrong in the proteins, and you get a defect. That's a mutation when it's wrong in the genetic code. All right, and that is it for your notes. I do not have any written work for you today, so I don't think I do. Let me look at my book here. Today is the 15th. Nope, it was just taking those notes. So I got no written work for you guys. Enjoy your Friday. Enjoy your weekend. Are we off Monday? Someone sound on. So according to my book, we're off on Monday, so I'll see you guys on Tuesday. Have a great weekend.